this map before we get to the analytic objects that will be involved. The units, the classical regulator, a reflex that we'd like to instill in one. So the reflex, whenever you see a lattice embedded into an interest in embedded, say, into an R vector space. So in an interesting way. Well, obviously that's a very vague way. And not simply as z to the n embedded in natural way to r to the n. Try to make sense of what's called the co-volume. The volume of r to the n modulo that lattice, let me call it lattice lambda. That's not wrong. And in our case, here we have, in a sense, we have two ways of two lattices embedded, two types of lattices. First one is can take OF itself, embedded into an R vector space of the dimension of the field degree, like K F over Q. That forms a lattice, and the co-volume is related to the discriminant, another fundamental invariant of the field. And the second one is OF cross, you see? And that's embedded into, yeah, as we've seen, R1 plus R2 minus 1, in a sense. Well, into a hyperplane in R to the R1 plus R2. And the co-volume has to do, well, it's the determinant of the vectors that are generated. So typically of a matrix with entries log absolute value of the unit, units say UI, and embedded in different ways. So that is an interesting number, and so the absolute value, just say it could be negative, of course. This is the regulator, the classical Durham regulator of F, OF. And so both notions, both co-volumes kind of will play a role in the formula to come. But maybe let's maybe one should say, remark, the discriminant, so this co-volume is actually rather, well, it deserves the name. It is rare to have two number fields with the same discriminant. Same discriminant. So two non-isomorphic number fields, obviously, what I mean. Isomorphic number fields. Same discriminant. And it's also a rare with same regulator. Now, the mini challenge could be can you find two number fields that are not isomorphic and have the same discriminant and the same regulator? So can you find, and by find in the extended sense, say Google or GPT, can find a number field with the same discriminant and regulator? Don't say the word. I know that you know, but okay. So this is an interesting thing, and maybe as a hint, yes, you can, but you have to go to a certain degree. It's not so obvious. Okay. So now the new ingredient that I already announced is, sorry, that was, yes, is a counting function. And and it's called, at least the first instance of it, the Riemann zeta function. Everybody will know that defined as beta of s some 1 over n to the s. And what most of you will surely know, so say real part of s at least greater than 1, then we have guaranteed that this converges, and the n runs through the positive. Yes. What maybe a bit less well known is it sees primes. How so? Well, let's try. Yeah, I think this one. The first instance is maybe Euler's proof that there are infinitely many primes. So, example, this one. Euler, already I think 1737, looked at this function for S real. Riemann then pushed it later on to complex numbers, which Euler did not really have at his disposal. So Euler looked at the real stuff, and he found if you take the fundamental theorem of arithmetic. Is everyone familiar with fundamental theorem of arithmetic? What do I mean by that? Every integer n is written as a product of primes in a unique way. The I to the I, yeah, unique. Say plus minus if you want, if it's in Z. That's what the fundamental theorem of arithmetic says. So instead of take the sum 1 over n to the s, you can also write it as the product 1 minus p to the minus s. And p runs through the primes. The claim is this is equal. Well, an Euler product. It tells you already corollary. There are infinitely many primes. So, is everybody familiar with this? Some of you, maybe. So, what happens for s equals 1? the left-hand side, what's called the harmonic series. The limit is this one. So we have diverges. So if we had only finitely many primes, then this would be a finite product, even for s equals 1. And yeah, that couldn't stand. So that's a simple way to see that there are infinitely many primes. But one can say more. There is a notion called prime number theorem. That was, I think, 1793 by a certain guy Gauss. He was, I think, 16 years old when he guessed that the prime number theorem should be something like the primes below a given, the number of prime numbers below a given bound x is something like x divided by log x. So he computed many primes already at this age. I mean, we tried to compute in the 100,000s or millions maybe. And then he found that this must be the actual law that governs it. And it was proved about 100 years later, I think 1899, by in parallel, kind of. Adamar was one of them, and Lavallée Poussin was the other. And they proved it, in a sense, using properties of the Riemann zeta function. Using the fact that zeta of S does not vanish on, say, real part equals 1. That was, and then it was, I'm still, it needed a clever trick, but that was the main ingredient. So we see again, zeta at the point 1 tells us infinite many primes. If we know more about it, say on the whole line real part equals 1, that already tells us a lot about the distribution of primes. And then, of course, there is the famous Riemann hypothesis, which says that the non-trivial zeros, if we analytically continue, I should have maybe said, maybe I should have said those properties first. Yeah, so yeah, a number of properties, important properties, before I go into important properties. So the first one, can analytically continue to almost every point in C, analytic continuation, to see that the only point that's left out is the point 1. At the point 1, 1 has a pole, and not just a pole, a simple pole, so vanishing to first order, and of residue 1. Residue 1. So reasonably well behaved at point 1. Another, and of course we have a functional equation. Let me maybe the freak is there is a functional equation. So if we write psi of S as a product of zeta with 2 factors, pi to the minus s over 2 and gamma of s over 2, and then zeta of S, this is symmetric in S goes to 1 minus S, is symmetric in S replaced by 1 minus S. So once we have analytically continued, then it makes sense to talk about the zeta s and also psi of s and the negative real part of s. And then this is symmetric. So that was an important finding of Riemann. So it has to do with maybe the theta functions having modular properties, or you could use it to what's called Poisson summation formula, lattices. So in a sense, has to do with Fourier analysis. So we can make sense of zeros, and the zeros, the trivial zeros, are four trivial zeros are zeta at s equals minus 2k, and k runs through the integers minus 2, minus 4, so on. Then there are trivial, the trivial zeros, and the non-trivial zeros are all expected to lie on a line. Line, and of course that's a famous line, real part of S equals 1/2, which is exactly sort of the center of this mirror symmetry, S goes to 1 minus S. Okay, well, not mirror symmetry, yeah, but I'm sure you understand one. Okay, so I think that's all. And there are, of course, the explicit formulas. Maybe I'll skip those. So or I indicate a fourth part where it's even more precise what the Riemann zeta function sees. When you look at these non-trivial zeros, and you have sort of a test function evaluated and take the sum over all the evaluation of that test function at the point where zeta has a 0, that is translated by some kind of Fourier transform to a sum over primes. The sum of the zeros of Riemann zeta, non-trivial, corresponds to summing over primes, somehow of the corresponding Fourier inverse function. But that's maybe too much is said here. And by analogy, for a number field, we have a similar construct. And that's given by Dedekind gave the ultimate formulation, but Dirichlet was the one who actually constructed this for quadratic fields. So you should probably also get credit. So for a number field, F number field, we put zeta f of s as, let's say, product, not the product, the sum. So what would we like to do? We'd like to take the sum over all integers in that memory. And will be just like what we did here. Sum over all, say, positive integers, but we could also take the negative one. And then raise it to a power. And then hoping that we get enough information by doing it for sufficiently many different s's, we get enough information on the integers themselves. So we try to see the integers kind of as the roots of an infinite polynomial of sorts. Yeah, maybe I should formulate that better. But here we cannot do that. In general, you have too many occurrences of the same thing, like up to units, to get divergent factors. And what one does is instead one takes all the ideals, so maybe a to the power s, so where a runs through the non-zero ideals in our integer ring of integers O And again, this converges for a real part S greater 1. And we get similar good properties. So maybe I'll try to contrast what we found for Riemann theta. Similarly, good properties. So analytic continuation is not obvious, and that was not found by Dedekind, but considerably later by Hecker. While this was in, I think, maybe late 1800s, 1890-ish. Hecker later on in 1970, recall correctly, we found the analytic continuation, again to C minus 1 at S equals 1. S equals 1. We also have a pole, a simple pole. And third, there's also a functional equation. This time a bit more complicated because we have both real and complex embeddings. So if we put gamma factors, a real gamma factor of S as same one as here, so this pi to the minus S over 2 times gamma of S over 2, and the complex gamma factor is 2 times 2 pi to the minus S times gamma of S. You just scale the S here by 2 and the pi also by 2. And then you get an extra factor 2. Then the psi f of S, which is the product, we have the discriminant of F. I think maybe absolute value just to be on the safe side to the power S over 2. Then we have gamma factors, the real gamma factors to the R1, the number of real places, and gamma of complex, half of the complex, no, exactly the complex places, gamma C of S to the R2. Yeah, that was the word I was looking for, the places instead of embeddings. So there are, for each place you have 2 embeddings. Then this satisfies in the same way, is symmetric in S replaced by 1 access. So very similar story. Ron, you look so critical, so no? Good. Cool. Thanks. Okay, but so what's different? I left out one of the statements that was made there. And that's kind of the punchline of today's talk. Now this time, I didn't say anything about the residue. Oops, hello. Here I said simple pole of residue 1, boring. This time, residue S equals 1 is really interesting. So what is it? That's the famous theorem. The residue at S equals 1, zeta F of S, is, so what do we have? I think we have denominator delta F square root. of delta f. We have that number W1 of f, the number of the roots of unity. Let's recall of roots of 1 in f. Then we have a power of pi. I remember 2 pi to I don't remember. Does anyone remember? 2 pi to the R2 and 2 to the R1. As simple as that. Yeah, you can think of the R1 takes sort of the interval between 0, 1, -1. So interval of length 2 in the real line, whereas this gives you 2 pi, well, yeah, so it's the circumference of the unit circle to the power of R2 times, and the most interesting part is the size of the class group F, which we called CL earlier, right? The ideal class group. Times the number that I haven't given a name to, let me call it regulator, reg1 of F, where reg1 was this number determinant of log of roots of units that gave us sort of the co-volume, right? In other words, the co-volume of phi of f of the units of f under that number that we wrote down. So if we recall, so this pertains to the units in OF cross. So really important arithmetic information. This is the ideal class group of F, of OF or of F. Another very important arithmetic data. And the product of these, apart from, so this is just fudge factor. Just you can essentially ignore this for the time being. So the Riemann zeta function, the Dedekind zeta function at s equals 1 sees the product of these two ingredients, so the size of the units. So you can think of these co-volume of the units. So the size that we attach to the units times the size of the class group. Mind blowing. Anyway, for me, it's still a miracle. I mean, it's just amazing. Okay, so absolute value. Yeah. So this is sort of the famous Dirichlet class number formula. Maybe I should I just bring it class number formula. And this was around I think 1890s for the quadratic case, and then later on by Dedekind for the more general case. So the point now is, can we take this mind-blowing fact and push it further? So let me just give a hint. In fact, we can formulate it in a reformulate. And looks much prettier with linear function equations. Theta of S. Then on the left-hand side, you have what's called zeta f star of 0. So function equation takes 1 and replaces by 1 minus 1. And this, by definition, is the limit of zeta f of s, which vanishes at s equals 0 to a certain order, and the order is precisely R1 plus R2 minus 1. So exactly the rank of the units. Right, so just recall this. exactly the rank of the units. And this is a phenomenon that we'll hopefully see tomorrow in similar contexts, but for higher, for higher cases. So the vanishing of the zeta function somehow also has to do, it sees more, not just the regulator, it sees even the rank of the units, kind of. And so this is now equal to minus the class number, which is called CLOF, or sometimes abbreviated to HF, maybe I should have noted, times the regulator, divide by this small thing, W1 of F, number of roots of unity. So essentially the product of class number and regulator. That's what this function C at 0. And so the question that poses itself is that special for S equals 0? Question, is this special to S equals 0? And the answer, of course, is no. We will aim to generalize. Well, to an extent generalize, but it's clear that it's a phenomenon that has very similar avatars for other cases. And in order to do so, let me prepare a little. We need to think of these two ingredients, so class group and regulator, as of CLOF, and regulator or units, like 1F slash units. So not divide, so or as first pair in a sequence. Of abelian groups. And the foreshadowing remark is, these can be seen as called K0 of OF. So the zeroth algebraic K group, which happens to be isomorphic to copy of the integers plus that class group of OF, and K1 of OF, and K1 of good ring is typically just the unit in that ring, OF cross. So the question will be, so what should so here we take sort of the torsion part only of the first group for our universal class number formula. What should be the higher K? So I don't know whether it's worthwhile starting today or rather postpone this tomorrow. Half an hour. Oh, okay. Well. Okay, so let's try to what should be the higher K groups, and also we can ask about are there can we think of these as think these as higher magnetic invariance. So in topology, people found groups that fit into exact sequences with those the corresponding groups K0, K1, also for residue class fields for sort of localizations. And maybe one should mention yeah, so a brief outline. Find this here. I think in 1968, it was known what to take for like K2 of a number ring or of a field first. K2 of a field is easier, and then there's a somewhat derived notion is K2 of the regulators as the kernel of a certain important map. And people like Milner, I think maybe that was Whitehead, then Matsumoto, Steinberg, Milner, and yeah, maybe it can help if he's not asleep. But yeah, forget anyone. Okay, see God. What she's out? Oh, 68. Well, that's when Milner's book came out, right? 68 around, or 70. So I guess that was the time when it was so active. And it's in 70 actually, yeah, already Quillen came along. So maybe I have to predate a bit. Okay. Okay. Anyway, so people had an idea what these groups should look like.
But again, I will need to put the name of Matsumoto in it.
I should not. Okay. Okay. Of light by thumb.
The paper of Matsumoto is the balance. Sur les groupes algébriques déployés, semi-simples évoluent. Algebraic group and lifting of algebraic group and giving a cell lifting of algebraic group. But of course, I mean, it is so we are in a setting which is almost the same as worked out in the book of Milner. But
you think he had nothing to do with it? He
no.
Found something that was
yes.
incidentally related.
Yes.
But it made its way into the presentation of K2 of F that everybody now calls Matsumoto's presentation. So it feels awkward to leave him out, and then later on. Okay. Yeah. Yeah. Thank you for the comment. And then we had, I think 1971, Garland showed that K2OF is finite. So let me know, I'll define it maybe tomorrow. Then at the same time, 70s, of course, there were several approaches, one by Quillen, one by Swan, one by that will be Villamayor. And Quillen took the cake by also proving important results. So this was the he gave even two constructions and important applications, which the others I think did not have. Applications, for instance, to finite fields. Yet these was able to define not only the K groups, but to determine what the corresponding finite field K groups are, and finite generation for number fields. Well, so while Garland showed the finiteness, but he for that very specific group, Quillen showed it for number fields. Finite generation. Finite generation. Right. Generation of K2 of Kn of OF, n greater or equal to 3. But what he didn't give was the exact rank. Borel, in I think 74, gave a precise rank. These groups, which I haven't defined at all, these groups. But I think you don't want to see the definition unless, well, yeah, it's a rather abstract one. And we want to see a very concrete version of those instead. Saying that the rank of K2n of OF is 0. Rank K2n minus 1 OF is one of two things when n is greater or equal to 2. So it's either R2 for n greater or equal to 2 even, or R1 plus R2 for n greater or equal to 3 odd. So it's and the case where n equals 1 is what we saw in a sense, slightly the distorted version of it, the K1 OF as rank R1 plus R2 minus 1. And that has to do with the pole of the zeta function, which is not there for the higher evaluations of zeta. Okay, so maybe this is kind of foreshadowing of what's to come. And now the next case, here, let's aim for tomorrow. To make sense of the following statement. Tomorrow. This is due to make sense to the Liggenbaum. Now we have generalization of the Dirichlet class number 4. The zeta f star, again, the first non-vanishing term in the Taylor series expansion, as we had previously, we have taken the limit divided by the vanishing order at this point. So the zeta f star at -1 up to maybe a power of pi, I think maybe R2. Is it equal to something like the size of a higher K group divided by another size of another higher K group times co-volume of well, actually the same K group as here in the denominator. So here would be K3 OF. No, sorry, here would be K3 of OF. Here would be K2 OF. Finite. It will be finite, and it will play the role of the class group, the ideal class group, which is finite. that has an avatar in K2OF being finite. This one is sort of higher roots of unity, higher roots of unity. So this is the torsion in that group K3OF. And here's the volume of K3OF. So it's the same story as before, where we had seen a zeta of 0, we have star of 0, being the product of a class group times a regulator. So here we can call this a higher regulator, the second regulator. Here we call it the higher class group. And we can think of the K3OF replacing K1OF, which were the units. So these are, can think of high regulators on higher units. So the same picture, and here like the torsion in K1, meaning roots of unity. So we have higher roots of unity. The exact same thing, possibly up to a factor of power of 2, was Lichtenbaum's question. Is there such a formulation of sorts that generalizes the Dirichlet class number formula? And so tomorrow we'll try to give an explicit version of the corresponding higher K groups, especially of this one, and then maybe also guess what we can do for CDF star at -2, -3, and so on. It should be a phenomenon that should be true for all negative integers. And yeah, so maybe that is a good point to see for us. Yeah, thank you.
There is a long time, I think some while ago, Fritz Rubenbart conjectured that this class number formula can be generalized at least to finally generated with quotients, if not to consecutive. And of course, you have to interpret all these ingredients in a nice way. The zeta function is the zeta function of known subgroups or subgroups. Class number is interpreted as number of isomorphism times of the profiler coefficient, and the rest sort of modifier, but it's completely open or.
But would you be able to find that formulation? I think that's a very interesting. Okay. Oh, in his mind, you think? Not in.
And it got sort of pointed that way. It has never been formulated in the paper as far as I know. And Grunewald himself.
Yeah, okay.
But it's certainly, I mean, Grunewald's suggestions are always interesting.
Oh, great. The comments?
When you say size there, just the city, what do you mean by size? I mean,
Size of finite group. So,
no, okay.
right?
Yeah.
So this will be like in as I said here, Garland is finite. So that's an integer, will be a finite
For 2. Oh yeah.
for K2.
Oh yeah.
But then the rank of this is always 0, and it's finitely generated, so it will be finite as well for any higher one. So we will always have an integer here. This also will be finite, and then here we get sort of higher class groups of higher regulators, and these higher regulators will be replaced. I mean, the log will be replaced by higher logs. They're called polylogs. So it's really very similar in nature. Complaints?
Oh.
You will tell me.
I will speak about hierarchy in my talk.
Okay.
I will give maybe a short overview of the history.
And the more correct one.
No, I have truly. You have true comments. Okay. Then Okay, I understand why you want to first start from theory with the setting. But would it be easier to refer to look at the regulators from the viewpoint of Benson building homology? Is it easier? No. For you, it is not.
It's not, no, because I mean, I cannot really pinpoint the Bayesian cohomology. I mean, the differential forms, would you be able to write them down and work with them? I cannot. So here in this setting, no.
Okay, I agree. From the explicit
yeah.
computation viewpoint,
yeah,
I agree. But from the formalization,
yeah, conceptually, of course, it's much better to look at Bayesian's big picture. But yeah, that will not help me in making it explicit. Yeah, I agree.
And we in 10 minutes. We're on schedule now for a regular lunch break.
Ah, perfect.
So,
So
there are no more questions.
yeah.
So, thanks again.
No.